recording. All right, so sorry, say it again. Welcome to our class again. And like I just said, I want to clarify some quick issue about the exams. I have received all the exam papers and I'm in the middle of grading right now. I see some common problems from the exams and I'll reach out to some of you if there's issue with your potential grading, okay? And I expect to get them all done by Thursday, and that is my target. If not, latest on Friday this weekend, I'll definitely get them done. And sorry for dragging my feet on it. I have 63 exam. I finished about 1/3 of it, so I still have 2/3 to go. Okay, now one student or two have some trouble with starting time. Somehow they remember the wrong starting time. And I believe we have corresponded individually. So please stay behind after lecture. So let's talk about some mitigation plans. All right. And you know who you are. So please just stay behind. Okay. All right. So let me shut up and turn the table around asking you folks any question about the exams and the courses so far. Anything? Anything? Are we all happy?
Yeah, it was
All right. Yeah.
pretty good.
All right, good. Okay, so let me get back to the main content. Okay, that is what we're here for today mainly. And like I said, there's no homework last week due to the exam. All right, so you had a break, but we will have homework this week. And also for your information, you should know that your quiz number 4 is due. Okay, quiz number 4 is due this week, I believe. So if you haven't finished that, please do so. All right. So today we're going to talk about new content. All right. So before I start, let's just quickly review what we have done. Right. Oath story again. Right. What we have done before. So first of all, again, if you join, please mute yourself because I can hear you as a background. Thank you. And so what we have done before is a singularly reinforced section analysis and doubly reinforced section analysis. So I'm just going to draw them apart so you can see them simultaneously, right? So for the singularly reinforced section, we just have a old-fashioned concrete block and have a reinforcement at the bottom here, AS. And what we talk about is that essentially we have to balance compression equal to tension. Anything? Can you guys still see the screen? All right. Like I said, once you join, please mute yourself unless you have questions or something to say. All right. Thank you. And then the moment capacity MM is equal to C multiply over T. Either way, they're the same. T multiply JD, where JD is roughly equal to, well, in this case, not roughly, but equal to ds minus half A. All right. So that's all about singularly reinforced section. Okay. Now for doubly reinforced section, the difference is that not only we have the bottom tensile reinforcement AS, we also have the compressor reinforcement AS prime. All right, so in this setting, we have to balance more. So T, the compression equal to tension, but the compression has two parts. One is compression from concrete, CC, and the other concrete compression from the steel, CS, and that equal to T. That equals T. And also the moment changes. The moment changes becomes CC multiplied by ds minus half A. That's fine. Plus what? Plus CS. Sorry, where is the CS? This is steel, right? Steel, right? And this is ds minus ds prime. ds minus ds prime. Now you notice that all of the moments in the doubly reinforced section were summed with respect to the tensile reinforcement. Was summed with respect to the tensile reinforcement. And of course, there's still a JD, but in this case, we have both components of compression forces from the concrete and steel. So we don't really have one lever arm. Instead, we have two lever arm. So if you really look at it, I mean, really look at the core of it, that's it. That's all we have learned so far, right? For the design part is essentially how do we do design, right? When we do design, essentially is that we don't know T. Well, let me just clear it. So design, so this is analysis. So let me extend it. for design, right? For design, and this is design with given geometry, okay? For design with given geometry, all we're trying to find is AS. So all we're trying to find is AS. So what we do, we get that C equal to T, that equals ASFY, that is assume the steel yielded. Go back to find AS, okay, select the bars, and essentially repeat analysis. Oh, sorry, my spell today is a little bit awkward. Analysis, right? Repeat analysis. And that's what we did for singular reinforced case. And for doubly reinforced case is slightly different, right? That is, we have the split moment, Mn equal to two component. One is from a singular reinforcement, right? And the other is from the doubly reinforcement. So we have to determine the doubly reinforcement part, the compression part, by using mu divided by phi minus mn1. But the rest is the same. Okay, so that is the design for singly and doubly reinforced section with given geometry. We also talk about how about unknown section. Right? And this is exclusively for singly reinforced section. Not the doubly, okay? Not doubly. So for unknown section, what we do, remember, we have to introduce a row initial roughly equal to beta1 divided by 4 f prime c over fy. Okay, that is row initial, and we have introduced omega rho fy f prime c, and we have introduced r, which is blah blah, right? You can recall the nodes, right? Okay, but what we have done is that we introduce these three parameters, right? And then eventually we coming down to a simple equation that we say BD squared has to be greater, BD cube, BD squared has to be greater or equal to mu divided by alpha phi r. So there is no alpha now yet. Mu over phi r, right? And now we say assume the ratio between the width and the depth is alpha, then we can get d cube, or d has to be greater or equal than mu alpha phi r to the power of 1/3. And that's how we estimate depths. And mind you that this depth is ds. Okay, that is ds. Then with the section given, what you do, you essentially go back. So repeat design with given geometry or given section geometry. Okay, all right. So if I really want to play this around, just like boxing, right? And I want to name them, say this is section 1, right? And this is section 2, and this is section 3. All we have done is that 2 is built on 1, 3 is built on 2. And this is how we end up doing our design for singly and doubly reinforced section. Okay. All right. So you see, it's not complicated. It's quite pleasant actually, because it's straightforward. And this has been tested in exam 1. All right. Now, if you still have trouble understanding this, you want to reach out to me after exam 1 grade is released. Okay. We have to have a serious conversation about it. But now I assume we have got this under our belt, right? We all got this covered. Now let's move on. So with this, we are a little bit audacious. We'll say, let's get a little bit more brave, and we're going to design a different section now. So lecture 9, we're going to introduce a next step. The next step is to design a T-beam design. So everything is same except that the section has changed. So objective one is understand the stress distribution. Folks, give me 1 second. I really need Sorry, I'm back. So understand the stress distribution in T-beams. Okay. And obviously that goes without saying that the stress distribution in T-beam is different from stress distribution in the rectangular beams, as we talked about before. Okay. And the second objective is to design T-beam. Design T-beam. All right. So this is our new topic. Okay. Now we have graduated from the rectangular section. We have graduated from rectangular section. All right. And then, so the question is, what's the difference, right? What's the difference? I mean, it's just a shape after all, right? How can it be so different? Nah, it's just gonna be same, right? You know, that's what I thought, but turns out different. It's not that easy, simple, right? So let's take a look at the stress distribution in the T-beam. Stress distribution in a T-beam. And of course, first of all, let me draw it out. What is a T-beam? So this is a T, right? This is a letter T. And I have some names to give, right? I say the effective width now, BE, okay? Effective width now, BE is bigger or larger than the effective width at the web, BW, okay? At the web of BW. Now, some of you may also see a symbol of BF, flange, okay? You may ask where we get this BE. I'm going to show you, but they're the same thing for now, right? If you see a BE and you see a BF, they're the same thing, okay? And also, since we have a flange, so we have a height of the flange called HF. And of course, the total height of a section from top and bottom, total height of a section from top to bottom is called H, height, right? And just to label it, this is the flange. This is the flange part. And again, the depths, if I have bars here, the depth is listed, shown here as ds. Okay, so that is the typical T section. And again, you may ask, again, what is BE, right? Effective depth, effective width, not depth, effective width. Okay, this is because in the T-beam design, we normally don't deal with single T-beam. They're usually together. And they're usually together in a fashion that they're connected by diaphragms. So their flanges are integrated. So it's very hard to say what is the width of a single section, isn't it? So how do we divide them? Is that we divide them by the effective width of BE. Okay, effective beams width of BE. And of course, right, this is in the middle, so it looks very straightforward. What if I have something at the end? So this has become the L section, right? Oops. Let me draw a little bit further. So this becomes an L section, right? Now, what is this, right? Okay. So all this has been specified in ACI code, which we'll talk about next lecture. Okay. How do we decide determine what is the effective width of a T-beam like this? Okay. But that is where the term effective width coming from, is we have determined the section. Right? So now we have the section T-beam here, right? T-beam here. What is the difference in terms of stress distribution? Okay, so before, let me just do a quick review again. What is the stress distribution for a rectangular section? So let me draw it here. So this is our old friend, rectangular section with the bottom tensile reinforcement here. And I have height of H, of course, and width of B. All right, and we know the strain distribution, always draw strain distribution is like this, and epsilon Cu, which is compressive strain, equal to 0.003. And the strain still is epsilon S here, right? And we know the stress distribution goes like a Whitney stress block, right? So what is a Whitney stress block? That has a rectangular stress distribution instead of parabolic, which all of you got it right from the exam. And I have a effective strength of 0.85 F prime C. And I have a yield strength for the steel, yield strength for the steel as Fy. Oh, actually, the error is wrong way, this way, Fy. Okay. And now this is the side view, right? So this is strain, this is stress, but all these are side views. What is the 3D view, right? So 3D view goes like this. So I draw my section, and this is the rectangular section from a 45-degree isotropic view. And I want to draw my stress distribution, right? So this is H, which is the height, and this is the width at the bottom here, B. So the stress distribution for rectangular section is actually a volume, right? And it follows like this. It's just like a block. And now this is a parallel line here. The width of the block is 0.85 F prime C. And the height of this block is the effective depth A. So this block is looking like a volume, right? So I'm just going to shade it, right? Volume. Okay. So that is how the block looks like, right? And also in addition to that, my tensile reinforcement at the bottom here, since it's Fy, right? Fy is going to be a Fy bar sticking out, goes this way, and that length here, ladies and gentlemen, that is Fy. That is Fy. Okay. All right. So this is the 3D view of stress distribution. 3D view of stress distribution. So you can see it's pretty interesting, All right. Now, what will happen if I have a T-beam? So let me draw the T-beam out. And just to get some similarity, I'm just going to say, you know, the T-beam is something like the rectangular beam. And this is not necessarily always the case, but just to make it easy on us, we'll say it's more like an extension of rectangular beam, but we let the web width BW maintain the same, and the flange be effective width like this. So the height HF like this, and just say the height stay the same, H, and that's it. So as you can see immediately, you say, oh, okay, I see, Bob. So only difference is that I added two more portion, right? The wings, right? I call this the wings, right? The side part, the side block, right? So that's the difference from the cross-section view. And from the strain distribution point of view, it's just identical. Strain distribution is identical. So epsilon Cu here, 0.003, and still here, epsilon S, and this is strain. Right? This is strain. But now, we have a little bit problem for stress. Okay? We have a little bit problem for stress. Why? Because we may have two situations. Right? Okay, so Whitney stress block dictates that when I have a stress distribution like a nonlinear shape, I can equivalently represent this using a rectangular block. Okay, and now that is to say that I have a actual compressive zone C, and effective compressive zone A. All right, effective compressive zone A. Now the problem is, what if A, which is the effective compressive zone, is no longer smaller than the flange height? Okay. Or in another word is, how do we compare, or what we will do if A is not contained in the flange? All right. So let's take a look at it, right? So there might be two scenarios in a T-beam, which is different from rectangular beam. So scenario one, okay, we actually have a case that A is smaller than HF. Right, let me just put a question mark here. But first of all, let's take a look at the easier scenario. A is smaller than HF. So when A is smaller than HF, things are easy, right? Because I have my section like this. And after I do my Whitney stress block, I see my compressive zone, effective, that is compressive zone, is within the flange. Is within the flange. All right. And remember what we said before, the tension side of the concrete section has no tensile stress, And we always say that we rely concrete to provide compression, the steel to take care of tension. So when I have my effective compressive zone size A smaller than HF, I might as well just treat it as a big block of section with a width of B equal to BE. B equal to BE. Isn't that? I mean, it's just essentially just like a giant rectangular section with the width equal to the effective flange width. If my compressive zone size A is smaller than HF, Okay, now this is scenario one. It's pretty straightforward. That is to say, if this happened, A is smaller than HF, then treat it as a rectangular section. Oops. Treat it as a rectangular section. Okay, so the stress distribution is the same. Okay, sorry, strain distribution is the same. That is, concrete fails at 0.03 and the stress is still like this. So I can still use my Whitney stress block. And this is 0.85 F prime C. And I have my A is right here. And my internal forces goes, this is concrete compression CC, and I have a tension of T equal to ASFY. So it's pretty easy, right? So MN would equal to CC or T. In this case, let's just use T multiplied D minus half A. And to be done with, in D is essentially the depth of the section. Okay, nothing changes. And to make it even more specific, the T, concrete compression C, equal to T equal to tension. So ASFY or 0.85 F prime C, A, B, E, effective, right? BE, remember? It's just like a giant rectangular section, and that is equal to ASFY. So this just converted back to the singular reinforced section with a rectangular cross-section, right? So this is easy, right? Nothing changes, no difference, essentially, no difference. But we might also have another scenario. Right? So let me move this line somewhere. My drawing today is horrible. Scenario two. What if my A is bigger or greater than HF? Well, actually, let me put the equal sign there. So this just becomes greater than HF. Okay. What if my effective compressive zone A is greater than HF? Right? So in this case, I can tell the answer right now. You cannot then treat the flange or treat the web and flange separately. How? This is how. Okay, so the section still looks the same as before. Okay, but I want to show you the stress distribution. All right, now if I draw a side view, which is 3D again, okay, 3D again. For scenario two, for scenario 2, my stress distribution in the flange, sorry, in the wings, right? Remember what we called this part is the wings. In the wings is different than the stress distribution in the web. So I can actually draw them separately. So for example, this is in the wings. So I can divide the section like this. I'm not going to draw my web stress, okay? I'm just going to draw my wings. So in this case, my stress distribution for the wings, I can just use the windy stress block. Okay? Use this windy stress block. All right, I have a horrible drawing here, but you get the drift. It's just block here, right? Block here, in compressive. And again, separately here, another block, compressive stress like this, like this, like this. Okay, and the width of it is 0.85 F prime C. Okay, and now the height of that is simply HF, isn't it? HF. So that is the stress in the wings, right? Stress distribution in the wings. Okay, now I need also add on the stress in the web, and now the web becomes like this. So I'm going to use the dashed line since these are already drawn. These are actual wings, remember? Okay, these are actual wings. Sticking out is the web here. So for the web, you treat them differently. Right? How? So here, the actual compressor zone C is somewhere here, and A is going to be somewhere here, just in the web. Okay. Of course, A is bigger than HF, right? So now I can draw the stress distribution inside web like this. Somewhere like this, right? So now this thickness right here is still 0.85 F prime C. But now the height here is A. Okay, so this is the stress distribution in the web. Okay, so that is quite different. All right, so this is the 3D view of the stress distribution. So I have to separate them. Both. Okay, so when I separate them both, right, I want to look at internal forces. Okay, so you can keep this still. Okay, I call it wings, or you can call it flange, just like in the textbook. They're the same thing. Okay, so I want to take a look at their forces and moment, right? So for flange, since I'm looking at this section right here, okay, what is the total force by the flange, right? So C, which is compression from concrete, CC, flange, just from the little side block wings, right? That equal to 0.85 F prime C, basically the volume of these blocks, right? Volume of these blocks, and multiplied by the HF, which is the height of this block. And now multiply by the width of the block. What is the width of the block? It's essentially this fellow here at this fellow here, right? And that, ladies and gentlemen, is BE minus BW. Okay, so BE minus BW. In case you forget, this is BW, which is the width of the web, and this is the BE, total effective width. So that is the difference. So this is the compression force from the flange. Okay, now what I'm going to do is I'm going to split the steel, split the tensile reinforcement. into two components. So AS equal to AS flange, okay? AS flange plus ASW web, okay? So part of the reinforcement, we let it to balance the compression force by the flange, okay? Compression force by the flange. So if you're confused, CC flange is just write it out fully. From this moment on, I'm just gonna write CCF, okay? CCF, so for simple, right? So ASF equal to compression force from the flange, all right? So this tells me that TS or TF, which is tension from the flange, to balance the flange equal to ASF multiplied by FY, still yields, right? Equal to 0.85 F prime C and HF BE minus BW. BE minus BW. All right, so I can determine my ASF, which is the tensile reinforcement to balance the flange compression, equal to 0.85 F prime C, 0.85 prime C HF, and BE minus BW divided by FY. Okay, so we call this the reinforcement to balance the flange for the flange. Reinforcement for the flange, right? So the moment, nominal moment resistance, MNF, of nominal flexure resistance, MNF equal to ASF, then this is Fy, and multiplied by lever arm, which is ds, minus half of the flange height. Where did I get this? Because the center of the total force from the compression of the flange, right, has a distance here to the bars, somewhere here, equal to ds minus half of the flange, because it's in the middle of the flange, right? Okay, so this is the moment resistance or flexure strength come from the flange, right? So we call it moment resistance, okay, from the flange. Okay, from the flange. All right, so that is the web portion of it. That is the web portion of it. Sorry, that is the flange portion of it. Sorry, that's the flange portion of it. How about web? So web looks like this. Web looks easy, right? So the web, let's take a look at the look at the chart here. So this is A, that is the distribution, right? The total compression force is sit right here in the middle of it. So this is CCW, okay? And the distance between that and the bar, which is AS here, okay? And this is ds minus half A still, ds minus half A still, okay? So no surprise. So for the web, the compression force CCW equal to 0.85 F prime C A, which is the effective width as effective depth, compressive zone, and then BW. Okay, this is the critical part. It's only the web. All right. So the tension TW equal to CCW. So my ASW, okay, Fy, that is the tension force, equal to 0.85 F prime C A BW. All right. So the effective compressive zone A now can be calculated as ASW Fy divided by a 0.85 F prime C BW. Okay. And then the MN.
Hey, Professor.
Yes, sir.
I have a quick question on the flange portion.
Go ahead.
You have it written down that AS of flange equals CC the flange, but then later on, right below, you have it written down as AS equals the 0.85 F prime or FC HF EE minus BW.
Yeah.
Um,
So
how are those equal to each other if
right.
it equals CCF?
Right. So what it is that you have the total reinforcement as AS.
No, the equation right under that, ASF equals CCF.
You mean here,
No, the one that you were just circling, right below it.
right below, right here.
No, on the flange portion.
I mean here on the top.
Yes, in the flange portion, not the web.
Oh, flange portion. You mean right here?
I didn't
This
see
one
where it
or
was
this
marked.
one? Which one?
Okay, so the equation that's just written down is ASF equals CCF. Yes, that
Right.
one.
Right.
And then down below,
Mm-hmm.
the one that you're just marking, the next one down.
Right here, right?
No, still in flange.
Right here.
Still in flange.
Oh, still in the flange. Okay, so you mean here and here?
Yes.
Okay.
So that second one, the bottom one there, that is
Oh,
CCF
okay. I
divided
see.
by
I see.
FY.
I see what you're saying, right? So let me correct that by doing this.
Oh, okay.
Does
Okay.
that make sense
Yes.
now? Yeah, sorry about that, right? So I'm trying to say is that the reinforcement split in half now. Not exactly in half, but the reinforcement split in two components now, right? One part of it will balance the compression by the flange, and the other component will balance the force by the web.
Okay. Yes. Absolutely. Thank you.
Yeah, got it. Sorry about that. That's just a typo. I forgot to put it there. Okay. Okay, I think that clarified. Thank you for that. So the moment caused by the web, M on web, equal to AS W F Y and multiplied by distance ds minus half a. Okay, so this is the moment contributed by the web. Okay, all right, so this is the tension compression force balance for the web. That is moment contributed by the web. All right, so as you can see, they're different. They're quite different. They're quite different. Okay, and now to help understand this, right, we can then look at the design perspective, right? Design approach, right, for this. So the design approach basically says I have a stress reduction factor and I have the moment resistance from the flange plus the moment resistance from the web. When I add them together, the total design should satisfy the applied or factor moment. Okay. So that is how we design a T-section. All right. Okay. But as you can see, there are two scenarios, right? Two scenarios. One is scenario one right here. We haven't talked about anything about scenario one because if I find out that my effective compressive zone is smaller than the flange height, I can just design as a rectangular section, isn't it? With a web that B equal to B effective. It is only falls into scenario two where my effective compression zone A is bigger than the HF. I have to do my two parts calculation and take care of the flange, take care of the web, and then phi MNF plus MN web has to be bigger or equal than MU. All right, so this is the approach. Okay, so with this, let's take a look at an example, right? Let's take a look at an example. So 9.2 example on T-beam design. Of course, right? So this is only for known section. Geometry is known. Okay, so I have a T-beam and I have a flange width BE that is equal to 47 inches, quite wide. Okay, and I have a reinforcement right here, AS. And let's just say I don't know AS. I'm designing for it, isn't it? But I know that my flange height equal to 3 inch. Okay, and I have a distance between the bottom edge of the flange, to the entire section. Okay, let me just put this little bit on the side. You don't have to change much, but okay. So the distance from the edge of the flange to the bottom is 20 inch. So the total height of the section H equal to 23 inches. And now my depths, right? I give you the depths. Estimated ds equal to 20 inch. So that is the section, okay? And don't forget the width of the web is only 11 inches, only 11 inches. And I know my concrete, and my concrete F prime C equal to 3 KSI, pretty weak concrete, okay? And I'm gonna use grade 60, so Fy equal to 60 KSI. You should know that by now, all right? And let's design for reinforcement AS. Okay, that is Mn has to be greater than equal than Mu, where Mu equal to a 533 kip foot. This is given. Okay, to simplify the process is given. All right, so how are we going to do it? How are we going to do it? So solve, or let's design for it. First step is let's estimate. Let's estimate, okay, the required reinforcement. Just like we did for simply reinforced section, right? So we assume the phi equal to 0.9. Stress reduction factor is equal to 0.9, and that is tension controlled, right? So phi mn is greater or equal than mu, phi mn is greater or equal than mu, and as required is equal to mu divided by phi fy d minus half a. And mind you that d equal to ds, right? D equal to ds. Okay, so what we're trying to do is I already make the assumption here. So what is the assumption? I assume it is rectangular section to begin with for the first step. Okay, and now here's the difference. So with this assumption, I say mu should divided by phi fy. Now ds minus half a, right? In singularly reinforced design, we say JD equal to 0.9, isn't it? For rectangular section, but for the for T-beam, okay, is different. So we say JD for T-beam, we can let JD equal to approximately 95% of the depth. For rectangular beam, we say JD roughly equal to 0.9 ds. Of course, in our case, right? In our case, we select the T-beam. Although the equation was assumed to be rectangular to begin with, and let me be more rigorous. This is just to say, yeah, this is just to say scenario 1, okay? Scenario 1. All right, so that's how we're gonna start. So with this, I can continue on, say, okay, now I get my AS required. And that is equal to, what is MU? 533 kip foot. And I convert that to inches, so 12 inch per foot divided by 0.9 multiplied by 60 KSI multiplied by 0.95 multiplied by 20 inches. Okay, so my AS required, do the calculation, find out is 6.24 inch squared. 6.24 inch squared. And now I say I can estimate my effective compressive zone A. Okay, how do I do that? Because A now would equal to AS required multiplied by Fy divided by 0.85 F prime C. And now, ladies and gentlemen, this is the important part. Let's use the effective depth BE. This is again for scenario 1. What is scenario 1? To remind us is that we assume A is within the flange. A is within the flange. So with this assumption, I can bring the number, and this is 6.24 inch squared, calculated previously, and Fy equal to 60 KSI divided by 0.85, and F prime C equal to 3 KSI at multiplied by 47 inches, which is the effective width. Okay, and turns out my A after calculation is 3.12 inches, slightly bigger than the 3-inch of HF. Oops, what happens? What happens that we assumed for scenario 1 where A is smaller or greater than HF. Turns out after the calculation, it is bigger. Okay, so this is the saying cannot be designed as rectangular section. Not good. Okay, then we will pursue to scenario 2. Okay, and we'll talk about next lecture. Okay, all right. I think this is a good point to stop. So I'm just going to stop here, and let me do stop sharing. And if you have any questions, welcome to stay behind. All right, or else I see you on Wednesday. Okay, thank you very much.
Professor, just a quick question.
Yes, go ahead. Kyle first,
Uh,
maybe. Yeah.
Yeah, what was DS in that last section? I just didn't get it down.
You mean here in the depths wise?
I can't see your screen, but
Okay,
yeah, whenever you're writing the or showing the. Yep.
let me share the screen again so you can see it. Is this right here?
Yeah, but on your diagram, I didn't get written down what the number was.
Right here.
Yeah, 20 inches. Okay.
20 inches. But I mean, Kyle, we did not use it yet. Just for your information. You see what happened is that we estimated.
Yeah.
Right? And the reason is that we don't really know where is my compressive forces yet. Right? That's very typical for singular reinforced section because we don't know where A or what is A, right? Because we need to know A to get the center of the compression force. Right? To be even more complicated for T-beam, we have two scenarios. So we assume scenario 1 to begin with, and we assume a JD, right? And then we just find out it is not scenario 1. Then we go scenario 2. That's when we start to use the DS.
Okay.
Okay, good. Yeah. Anything else, Louis?
Yeah. So I turned in my homework 4. I emailed it back to you.
I saw that. I haven't graded yet.
Okay. I was just wondering when.
Sure. Yeah.
You could.
Oh, definitely do that, right? The deadline is the I believe Thursday, right? You still got time, so I think you're good.
Okay.
Right? Okay.
All right. Thanks. That's kind of what I wanted. Mine's like towards my personal grade, so.
Oh, okay. Well, that has to wait a little bit, right? So we have to find out after first exam grade is out, okay?
Okay. Yep.
Yeah. Okay.
All right. Have a good one, Professor. Thank
Not
you.
a problem. Yes, sir. Anything else, guys?
I just had a question related with the exam.
Sure.
There was like one problem when we had like a beam, and there was like one part that had like positive moment and the other part has negative moment. And in real life, I mean, I know that whenever it gets to tension, like you should switch like the bars to the top because that will be the tension part.
Sure.
I mean, in real life, do you just have like, you know, like the bars coming on the bottom when it's like positive moment, and then you just kind of like switch them to the top once you get to the negative moment?
We don't switch. We don't switch. What happens is that you can design by section, right? So you can place a reinforcement and cut it off where you don't need it.
Okay.
Right? So you essentially place the bars at the bottom wherever the positive moment is, and place the bars in the top where the negative moment is. But the bars in the top, the reinforcement in the top will not extend it to the region where the positive moment is. Correspondingly, the bottom reinforcement will not extend into the region where the negative moment is. But since there has to be enough length to be buried to develop the yield stress, they will extend it a little bit, but not the full length throughout.
Okay, so yeah, so like they just kind of just switch from
partially,
from
right?
bottom to top.
Right.
Like,
yeah, we will talk. Yeah, we will talk about this scenario in a later chapter where we talk about the development lens. So you can just mark it down right now. Yeah, you can just mark it down right now. Say, see the development lens, and we'll definitely talk about that later. Okay.
All right. Awesome. Thanks.
Yeah, good question. No problem. Yeah. Anything else, folks?
Yeah, you asked me to stay behind.
Okay. Zach. Yeah, I know. Yeah. How about you guys? Rest of the folks, are you guys good? I need to stop recording because some of the question might